In this set of videos, we'll be talking about some basic properties of series because we'll be using series to solve differential equations next. And it may have been a while since you saw a series, so we're just going to go starting from the basics of just a definition of a power series. So a power series is an infinite series of the form f of x equal to some sum starting from index 0 up to infinity of a coefficient c sub n times x minus a raised to the nth power. What that looks like when we're writing out individual terms is we start with c0 times x minus a raised to 0 power, which is just 1, plus c1 times x minus a raised to first power, plus c2 times x minus a raised to second power, so on and so forth. And then sort of all the pieces of this equation too, I just want you to understand what they're doing. This first thing means that we're taking an infinite sum, we're adding a bunch of things together and never stopping. This c sub n is what we're going to call the coefficient for each term in that sum. And then this x minus a to the n means that we're considering values of x near a, and we'll talk about a later, raised to some power. And so hopefully you have some memory of working with series. This specific series that we wrote is centered around a for some number a. That means we always think about x as it relates to a when we're thinking about this type of series. And one of these power series is going to be a function of x. So once we plug in a and we know what our CNs are, this is just something that changes with different x values. And usually the reason we talk about series is because they can be used to approximate other functions. So for example, you might remember going over Taylor series. And they're just going to be this infinite series representation of functions. So for example, if you have e to x, you could represent it with this Taylor series 1 plus x over 1 factorial plus x squared over 2 factorial, so on and so forth. And that would be represented as an infinite series where we start from n equal to 0, go up to infinity, and we've got that x to the n over n factorial. So here our Cn is that 1 over n factorial, and our a is 0. But then otherwise it matches that power series form we wrote right here. And so if somebody wanted to roughly approximate what e to x is by hand or something, they would have 1 plus x over 1 factorial plus x squared over 2 factorial, and then they would stop at some point. So you could go out to 100 and have quite a good approximation of what value e takes on for any number x that you plug into that formula. So that's what a power series is. I'd like to talk about the reason we use it. So if you're still copying down exponentials, hit pause. But because many functions have this type of representation, they're going to be helpful for us to solve ODEs. As is often the case, our approach is going to be to plug series into the ODE and then find conditions for that solution to work. So the argument here is that ODEs have some solution that is a function, and series can represent functions in this form. So maybe if I plug a series into an ODE, I would get the series representation of whatever the solution is. And with that kind of introduction to what a power series is and why we're thinking about it, I'd like to talk about convergence. You're honestly going to want to come back to convergence a few times, so I'm going to go ahead and make that its own video. So I'm going to pause here, and then we'll move on to convergence in the next one.